So in this paper with Kelly Bergstrom, William Dodds, and Nicholas Lacosta, we measure the welfare cost of frictions. And to motivate the work, we start by observing that we know that frictions matter, right? So, for example, Shetty in 2012 has shown that frictions contaminate estimates of the structural elasticity of labor supply. But we know less about what are the welfare costs of these frictions. In particular, what we're going to be going after is a money metric measure of welfare. So we're going to be asking how much would workers be willing to pay to remove frictions in the labor market. And then we're going to try to see how much of this frictions willingness to pay comes from adjustment costs versus misperceptions about the tax schedule. And we believe it's important to disentangle those two things because they have different implications for public policy. So frictions that have as a source adjustment costs can be solved with policies that imply more flexible contracts, for example, fostering the gig economy, whereas frictions that come from misperceptions would actually be better tackled by measures that make the tax schedule more transparent for the taxpayers. So the setup we have is very simple. We have a worker that is choosing hours H, consumption C, and taking as given both his hourly wage W and the income tax schedule T. And he's gonna do so to maximize some utility that is increasing in consumption and decreasing in labor supply, subject to the constraint that he can only consume his labor income minus the income taxes that he pays in his labor income. And we're going to have two solutions to this problem. The first one is HF, which is the solution in the world with frictions. So those are the hours chosen in the world with frictions, the ones we actually observe in the data. And H star would be the ideal hours, so the hours that would be chosen if the worker faced no frictions in the economy. And this is going to allow us to define willingness to pay as the amount of money that we need to give to this individual in the world with frictions so that he becomes indifferent with respect to the world without frictions. So basically, because consumption is a numeraire here, this delta, which is going to be the variable measuring willingness to pay, is also going to be in dollars. And this is exactly the amount of dollars you need to give to the individual under his equilibrium in the worlds with friction to achieve the same utility he would achieve in the world without frictions. So perhaps it's useful to take a look at this definition in a graphical way. This is going to help us develop the intuition for the main result in the paper, or the main theoretical result of the paper. So we're plotting here hours in the x-axis and consumption in the y-axis, the numeraire. And the red line is plotting the indifference curve of an individual that we're also going to call CU star of H. Whereas the blue line is depicting the budget constraint faced by this individual, or C of H, right? And the willingness to pay measure, right, our delta, is going to be given by the distance between this blue dot and this red dot. Basically, this is because this is exactly the consumption. This red dot represents in the vertical axis, right? Like its value on the vertical axis represents the consumption needed under the hours of with frictions HF to achieve the same utility he would achieve in the world without frictions. And C of HF is exactly the consumption he ends up with in the world with frictions, because he cannot choose H star, he's forced to choose HF and be at a lower utility level. So we have this distance is precisely the delta that we want to estimate. So this is helpful because our willingness to pay formula comes from a second order Taylor expansion around the hours HF being equal to the optimal hours H star. To see this, we'll start with our definition of delta, which comes directly from the last slide. This is just the difference between CU star, the indifference curve, right, value of consumption, and the C of H evaluated at HF, right? So this is basically the difference between the consumption in the difference curve and in the budget constraint evaluated at HF. And then we're going to do a second order total expansion around h star. So this is going to be equal to the same difference evaluated at h star plus the derivative of this difference times the difference between hf and h star plus the second derivative of this difference divided by 2 multiplied by hf minus h star squared. Now we note that the values of the consumption in the world without frictions, right, under h star is equal in the indifference curve and in the budget constraint. This is coming from the tangency argument. And the same is true about the first derivative. So we know that the slope of the indifference curve, C prime of U star, and the slope of the budget constraint are equate at the optimum in the frictionless world. So both of these first terms, the first and second terms, are going to be equal to 0. And all we're left over is the third term that can be further simplified if we note that the second derivative of the budget constraint is equal to 0. So we end up with a simple formula that this delta can be expressed as C prime prime U star of H star divided by 2 multiplied HF minus H star squared. Now, C prime of U star is just the marginal rate of substitution, right? That's just the slope of the indifference curve. So if we take another derivative with respect to H, we can write the second derivative of CU star as the derivative of the marginal rate of substitution with respect to H. And that's how we get to this final formula in this first bullet. Now, to write this derivative, right, in terms of some recoverable elasticity, we would like you to note that the structural elasticity, the structural Hicksian elasticity of labor supply, which is defined as a derivative of hours worked with respect to the after-tax marginal rate, equals to the same derivative or log derivative of hours worked in the frictionless world with respect to the marginal rate of substitution. This is just coming from the fact that the marginal rate of substitution equals W times 1 minus C prime in this frictionless world. So this allows us to substitute out this derivative by this elasticity, and once we do some simple algebra, we get to this formula that says that the share of the total labor income associated to the willingness to pay to remove frictions from HF equals to 1 minus C prime, 1 minus the marginal tax rate, multiplied by the ratio between HF minus H star over H star squared, and 2 times the structural elasticity. So there are two intuitions that come from this formula. The first one is that this willingness to pay as a share of gross tax income is decreasing the structural elasticity, but it also is increasing in the square of the gap between HF and H star. So in order to develop a little bit more intuition, it's helpful to go back to the graph that we were discussing before, but now consider two different individuals. So the individual depicting the purple indifference curve has a small elasticity of labor, of structural elasticity of labor supply, whereas the red, the individual represented by the red indifference curve has a larger elasticity. And this is just capturing the intuition that someone that has more elastic responses to the tax schedule needs to have flatter indifference curves for this to work out graphically, right? And you see here clearly that as we move from a low elasticity to a large elasticity, the delta that we define as this distance between the indifference curve consumption and the budget consumption, the budget constraint consumption under the hours with frictions, actually decreases, right? It goes from the purple delta to the red delta, showing that willingness to pay decreases with this elasticity. Now the second result is that this willingness to pay increases with the square of the difference between the optimal hours H star and the hours with frictions HF. And to see this, we consider two individuals, both with the same indifference curve, same preferences or elasticities, and both maximizing their utility in the frictionless world at H star. But the individual A is actually forced to choose hours HFA, whereas the individual B is forced to choose hours HFB, so that this distance is actually twice as large for individual B as it is for the individual A. But you see here that the willingness to pay, right, the delta for individual A is less than half of the willingness to pay for individual B. So in other words, whenever we double this distance, H star minus HF, we increase the willingness to pay by more than twice. And this is capturing the curvature of the indifference curve, and is associated with the fact that this increase is proportional to the square of this difference. So now that we have this formula, we applied it using some surveys on actual and ideal hours. So both in the US and in Germany, there are surveys that elicit both the hours with frictions and our first attempt to measure ideal hours, which I'm going to call HI. So there are three questions in the surveys generally, right? So the first one is how many hours do you work? And the answer to that question is just going to recover HF. Second one is how many hours would you like to work? And that's our measure of HI, of these ideal hours. But then there's a third question that asks, why don't you work fewer or more hours? And these third questions help us filter out who did not understand question 2 correctly. So as an example, there are some people in the data that we observed that they say that they did not work fewer hours because they needed the money. Well, we interpret these individuals as saying that they are not answering exactly what we want. They are answering the question of how many hours they would like to work, holding constant their income. But what we want, what H star represents, is how much they would like to work if they accounted for the trade-off between labor supply and income. So we would take them out of the survey so that we get a better measurement for H star. We then calculate our deltas as a share of income, right? So our deltas over WH for several structural elasticities that we deemed relevant, the ones between 0 and 1. And we find two results. First is that if we focus on the US, Americans, for example, are willing to pay on average around 16% of their income to remove frictions whenever we set this elasticity to be 0.15, which is the estimated elasticity with the ideal hours worked in our data set. And we believe this is an important result because the results so far in the literature, they use much lower ratios for this willingness to pay share of total income. So it seems like it is at first sight that this willingness to pay is larger than what we believed previously. The second result is that even in models with multiple hours choices, endogenous wages, and dynamic decisions, we show that the willingness to pay remains pretty high. We have to make some small adjustments, but it never falls below 7%. So I'm plotting here in this graph, this structural elasticity in the x-axis ranging from 0 to 1. And in the y-axis, we're plotting the willingness to pay to remove frictions as a share of gross of tax labor income. And we are depicting in the red line here our favorite measure of this elasticity, which, as I mentioned, was 0.15. And in the blue line, we're plotting the means for these different elasticities. And you see here that for very low elasticity, this willingness to pay is around 23%. For higher elasticities is around something like 7%. In our favorite estimate for the structural elasticity, it is around the 16% that I've mentioned. The medians are always lower just because there are some outliers on the difference between HF and H star in the data. The next step that we take is actually to try to account for tax misperceptions. In particular, we're going to use some of the findings of this paper, this nice work by Rhys Johnson and Tom Bisking in 2020 that showed that 40% of taxpayers confuse average and marginal tax rate, the phenomenon that they call ironing. And what we do is that we use the perceived and the actual taxes and the structural elasticity to recover H star from HI and compute bounds under a more general model. So what I mean by this is that we go to the data and we use this difference between perceived and actual tax rates plus the structural elasticity of ideal hours to estimate how these individuals would adjust their income if they perceive the tax schedule correctly, right? And this allows us to further correct our measure of ideal hours, accounting also for tax perceptions. And then we're going to do the same that we did before, just plot this share of willingness to pay in terms of gross of tax income for the same elasticities. And what we find is that the adjustment costs are far more important than misperceptions. So we can just focus on the means here. So those are the blue and the green lines. The blue line is just the exact same line that we saw before. It's just the average, just accounting for adjustment frictions coming from the survey, the NSCW survey in the case of the US. And the green line is actually the same willingness to pay under different structural elasticities, but now also accounting for these tax misperceptions. And you see here that the share doesn't increase that much, suggesting that the most important source of frictions, it's actually adjustment costs and not misperceptions.